All right, so there is a mastering due tonight, if you haven't already done it. And our first exam is Wednesday. Yay! If you are going to take it either early or at the Academic Support Services, send me an email to confirm what you have decided to do. If you decide to take it over there, that's fine. If you decide to take it early, just confirm with me that we're still doing what we agreed to last week. That only applies to a few of you. But let's see. Since I didn't get any questions over the email, I'm assuming it went awesome with your practice test. And there's a question. Okay.
Okay.
Number one, take that off. It's a bad question. Yeah. Yeah. Sorry. No, let me look at the practice test. Definitely number one. Scratch out because that's not what I want. Oh, number three. We can totally do number three. All right. Number three asks which of the following are an atomic element. So first thing, let's double check what an atomic element means. Everybody see that okay? My mouse is in the way. All right, so atomic element is an element that's found by itself, not paired. Right, so if I have a single atom, it means it's all by itself, and so if I have an atomic element, it means it's an atom that's not found with a pair. The other version of an element would be a molecular element. So what do you have to be a molecule? You have to have two or more, right? Two or more is something. So if an atomic element is found by itself, a molecular element found with at least two atoms bonded together. That says least. That's crazy looking. Least. That made it worse. There we go. So the molecular elements we care about are the following. We're interested in all the halogens. All the halogens are molecular. All right, so all those guys are molecular. So everybody, F, Cl, Br, I, all found in a pair. The other elements that are found in pairs are going to be H2, O2, N2. Those are going to be our ones that are always found with someone else. They like being around elements themselves. They're always found in a pair.
So, atomic elements was discussed in chapter 3 because I went back and tried to find out what it is. So, should we have?
No. I brought it up a little bit in chapter 2 when we were talking about just the periodic table in general. But so, of the list that's on that question, what is it? It's nitrogen, fluorine. What are the other two things in that question?
Bromine, hydrogen, nitrogen, oxygen, magnesium.
So the question is, of the following, which one will be found by itself? Which magnesium is the right answer? All right, other questions off the practice test? Yes, ma'am. I'm going to say it's going to depend on what information I give you to solve for energy, right? So there's two different formulas we used. We had E equals hc over nu. We equals h lambda, right? We had those two things. Most likely, I'm going to give you a wavelength and ask you to find energy. But in theory, I could give you a frequency and ask you to find energy. So if I give you a frequency, you would use this one. And if I gave you a wavelength, I would use that one. Yeah.
Will you give us the values of the constants, or do we need to know those?
No, I give you all the constants. I give you all the constants, you just have to know how to use them. Other questions? Yes.
Okay, this is just in general. Is the whole thing going to be multiple choice?
So, I finished writing it just before this class. So it's looking like it's going to be about 1/3 multiple choice. So it's going to be about 1/3 multiple choice, so like 30 points of a 100-point test-ish multiple choice. A half, so greater than, I think it's like 50 points, 55 points, something like that. Short problems. So those are ones where you're going to show your work in some way. So maybe it's an energy problem, or maybe it's an orbital diagram problem, or maybe it's whatever kind of problem we've been talking about. Number of electrons that could be found in this orbital, right? And then I think there's going to be one, maybe two. I think I decided on two. Short answer, where it's going to be like, why, like, what's the relationship between energy and wavelength? In a sentence. You know, one goes up, one goes down, something like that. Or, what was the other question? What is constructive interference, right? Any of those, like, one sentence things that have been on your homework. So, it takes like a sentence or so to answer.
Okay, one more. How many questions altogether is it?
Questions all together.
Like 50, 100?
Whew, 100 would be crazy. I think, okay, I'm pretty sure it's 10 multiple choice. And then I think I decided on, I'm going to go with 12. 12 of everything else. The exam is designed so that the person who comes in and knows it can finish in 30 minutes. Then, if you need more time, and everybody should be able, you only have 50 minutes, so I can't ask 100 questions. That's because it takes, on average, takes you about a minute to do a multiple choice question. So you should finish all the multiple choice questions in less than 10 minutes. And then I'll give you the rest of the time to do everything else. So that's how I work it. Doesn't always go to plan, right? But that's my plan going in. So I figure if I can take the test in about 15 minutes, you guys can take it in about 30.
And we just can't have a graphing calculator, correct?
Correct.
Okay.
No graphing calculators. And I give you lots of space to work out your problems, but I'll have scrap paper if you go crazy and need to write a really long essay about constructive interference. I'll have spare paper, but you should be okay. The test, I can give you, so this is a test from who knows when. All right, the tests all look like this, where put your name. There's a pledge on here that says you have not cheated, nor have you seen anyone cheating off of you. You sign that if that's true. In this section, I give you all the constants. I give you a periodic table and a breakdown of points. So there's a test from a different class, but in general, right, lots of space, multiple choice questions, some either fill in the blank or like that's a short answer question. So, all right, other questions we got? Yes.
Is there something about paramagnetic versus diamagnetic?
No. It's fascinating if it has a lone electron versus a paired electron, but no, not on the test.
What was the question?
The paramagnetic versus diamagnetic. Super interesting, but
Also the exceptions of the ionization trends.
no.
I know it's tough in some
Yeah, I just
places.
want you to know the general rules.
So we don't have to know like those exceptions to the
Oh,
question.
right. So in general, the homework's designed to be harder.
Yeah.
The homework's supposed to be harder than the test, right? Because you have, in theory, unlimited time to do the homework. And you get 4 or 5 attempts on every homework question. So the test is super hard compared to the test.
mean the super.
What did I just say? Nope, that's not what I meant. Reverse that.
Okay.
Reverse that. The homework should be much harder than the test. So if you're able to go through the homework and say, I got this, no problem, the test should be, in theory, very straightforward. Yeah.
Yeah, I have a question. It's the, over the homework, I don't know if this is anything with this, but the problem where it's like, which one of these is a violation of this of the 3 principles? The Hunt's principle, the...
Off-bound.
Yeah.
Mm-hmm.
I don't know if you like have that. in
I
front.
don't have it, but I can make something up.
Okay, yeah, because there's a couple of them I just don't really.
All right, let's first define the 3 things, and then we'll see if we can come up with something that violates their rules. All right, so there's poly, right? There's poly exclusion. All right, this states that each electron in an atom has a unique set of 4 quantum numbers. Okay, then we have all right, we got Hund's rule. I don't know if you say the D or not. This says that we're going to fill the generated orbitals, spin up first. Then we have, I think that's spelled right. Aufbau's principle says fill low energy to high energy. All right, so those are our 4 rules. So let's see if we can come up with something. Let's see if I can come up with something genius to violate those rules. I don't know if I can do it all at once. All right, so let's say I'm purposely writing off screen so I can be brilliant when you see this. All right, so I have electron 1. All right, here I have my 2 electrons. Which one of these things is it violating? All right, the first one. All right, so I have 2 electrons with the exact same set of quantum numbers. What's one way I could easily fix this? Change the spin. All right, so I've changed the spin. This guy's now up, this guy's now down. How does that help us with Hund's rule? So if I have Hund's rule, like if I'm drawing, so if it's n equals 4, L equals 3, which orbital am I looking at? 4s, 4p, 4d, 4f, f. Okay, so I'm looking at 4f, which is a crazy example. I would never have you guys do this. But 4f would have 7 platforms. Right, ridiculous, craziness. So if it had 7 platforms, how would I fill them? Would I do it this way? Oh, what's wrong with that?
That's probably Hunt's.
That's Hund's rule, right? You have to do 1, 2, 3, 4, 5, 6, 7. You got to do all ups, and then you can come back and do some downs. Right, so degenerate means if you're picturing it as an orbital diagram, that the platforms all belong to the same letter number combination. Aufbau principle would be something like this. Let's say I'm going to write an electron configuration. What went catastrophic with this one? I'm missing the 2s too. I decided to fill the 2p before the 2s, right? Can't do that. We have to do it, how many electrons was this? 8, 9, 10, 15. So,
What did you say?
The TX2. Oh, yeah.
let's see, how many is that? 10, 3. Right, this would be correct. That would be crazy, because I skipped a level. And so alpha says you have to go 1s, 2s, 2p, 3s, 3p. Gets a little squirrely in there. Do some 4s's, then 3d's, then back to the 4p's. But in general, right, feel low energy to high energy. So this one is the alpha, this one is Hans, and this one was Pauli. Good, good. Okay, what other kind of questions do we have?
Regarding the experiment you went over, do we have to go with that?
No. So all the experiments, they had like people's names and dates and specificness. Fascinating, but not on the test. Yeah. Fascinating. I'd love to spend more time talking about it. Cathode ray tubes, super interesting. Einstein, the photoelectric effect, spend all day on it, but actually not on the test. Save it for physics.
We don't have to.
Okay, that's a strong statement. I would say they're not on the test. I wouldn't go so far as erasing them from your memory. That's crazy. Yeah.
Okay, so 16 on the practice, you have to determine the energy of 1.2 moles of proton per wavelength of 510 millimeters. Can we just go through the whole math?
Yeah, let me find that problem. Yes, okay. My notes got a little out of order today. Is it really hot in here?
Yes. Yes.
Okay.
Are you going to post this?
Yes, I am. So I did review this morning, so I'm going to post that. And I'm also going to post this, because usually I only post one video between the two classes, but since you guys are asking different questions, I'm going to post both classes' questions. So you can watch yours, and maybe the other class had some questions you guys didn't have. And if you have extra time to watch both, then you can. All right, let's see here. All right, I think I have it here. Get to a plain piece of paper. That's the one? Yep. All right. So what units did I give you? Right, I gave you nanometers, and where do you want to end up? Eventually you want to end all the way in energy, right? So this is a question about, we had two different energy choices. Since I gave you wavelength, I would choose the one that says energy is related to wavelength this way. I think that's the easier one. All right, on the test, I'm going to give you the constants. So, all right, H. And C is this. All right, so now you can do this in one of two ways. You could convert the wavelength from nanometers to meters first and then plug it in, or do it all at once. Both are fine, as long as they come out mathematically the same. I'm going to do it all at once, because I am a risk taker like that. If you know anything about me, you know that is the craziest statement I've ever said. I'm not a risk taker at all. All right, so if I want to get out of nanometers, do I put nanometers on top or on bottom? On the bottom, down here, for meters. I'm going to put it 1 meter. So which is bigger, a meter or a nanometer? A meter is bigger, right? So I need a lot of nanometers to make up 1 meter. All right, so let's see where that gets us. Times 3 to 8. 5. How many significant figures do I get to keep? 3. Which, in this case, the rounding's a little funky, right? Because it's 389 times 10 to the negative 37th. And it's really 9, 7, and 6. So I would accept either 8, 9, or if you wanted to round up to 9, 0. Both would be fine. Question first. Why is it 3? With this 3?
No, why is it 3 significant figures?
Oh, 3 significant figures. Gotcha. Comes from this one. Oh, and this one. Both of them are only 3.
Well, I thought you were going to take it to the constant. That would be 2.
Oh.
The 0 counts.
The 0 counts because I guess I didn't write it down. It should have been 5, 10 point nanometers. Yeah. This one. This one is 5, 10 point. Yeah, so that gets 3.
I thought it was just 5 on
Oh, sorry. Yeah.
Okay.
Yep. All right, so what units am I left in for my energy? Joules. All right, so that's step 1, right? Because that is the amount of energy per 1 photon. But now I want to know about more than 1 photon. I want to know about moles of photons. So we're going to take this. Could I multiply it by 1.2 mole right now? Would any of the units cancel out? No, I'd be in crazy joule moles, or joule per photon moles, or something crazy. So I had to use something. All right, so now my photons can cancel out. Now I'm in joules per 1 mole. What do I have to do to get rid of those moles?
And we're supposed to have our answer in joules, not kilojoules, right?
I would accept either,
Because the answer in the back is kilojoules, but.
which is fine. It just determined the energy, so as long as it's in joules, I'd accept joules or kilojoules, both would be, as long as the math is correct.
So
Either
like,
one's fine.
if the answer in kilojoules is 282, but if I got 2.82 times 10 to the negative 13.
That seems a little off. Let me check here. 3.89, 37 times 6.022, 23rd times 1.2. Oh, okay, no, that's right. Joules.
So that's very much different than 282.
Oh, is my answer key a little funky?
I don't know how you got 10 to the 37. I think it's 10 to the
Yeah.
negative 19.
I think
And then-
Oh, did I go wrong up here?
I got negative 37.
6.626, negative 34. Yep. You can't see it. I typed it in wrong. Negative 19. That makes more sense.
Oh, well, you just have that. Yeah.
was wrong up here. That should be negative 19. 6.626 negative 34 times 3 to the 8th. Divided by 5. Whoop. That's parentheses, so get you. My fault is I didn't have the parentheses in the right spot. Yeah, parentheses are tricky. Tricky tree.
You said we could also use what avocados are non-whole.
Yep.
Instead of doing that whole.
Yes, that would be fine too. Yep. So, great tip when you're doing it on the test. The more work you show, the more partial credit you get, right? So I didn't show any work between here and here. And so if I had just a flat out wrong number, I would have lost credit there. But then I used the wrong number to solve part B. You would get full credit for that half the test question. So, right, you went wrong up here. I can't count you wrong twice. So you use a bad number to solve the second half. But you solve the second half correctly, you get the points for the second half. It's just I'd have to penalize you on this. But if you'd showed me all your work where you multiplied that out, I could better pinpoint where you went wrong and give you more credit. So the more work you show, the more credit.
But, okay, I'm putting a parentheses on everything in that first step. I'm still getting to the negative 37.
I'll see your, look, I'm guessing it's your calculator. The way you're punching it, I'll figure it out. All right, we'll do it by parts. We can check it out. 6.626 negative 34 times 3 to the 8. Woo, not that. All right, so on top, 1.98 times 10 to the negative 25th. So 510 divided by, should be 5 to the negative 7th. 1, 2, 3, 4, 5, 6, 7. Yep. Yeah. So if you are seeing calculator issues, it may be better if you do it by parts. Just do the top, then just do the bottom, then show me the difference. Maybe TI will give me a credit for showing their calculator all the time on YouTube. Get a free calculator. All right, how about some other questions? Since we've solved this one, probably. I could create some questions. Does anyone have any question about the problems at first? Yeah.
Has somebody's ever gotten on number 11 how to predict the charge of an ion?
Oh, let me see number 11 real quick. All right, this is good. So let's say I'm going to change it up a little bit. All right, so let's say I have the following elements. Let's predict what charge or what kind of ion they would produce. Let's say, let me come up with a few. Let's do this one, that one, this one, that one. Okay, so I got fluorine, calcium, sodium, and oxygen. How many valence electrons does fluorine have normally? 7. It has 7 valence electrons. Is it likely to lose the 7 valence electrons, become some positively charged guy? Or will it gain 1 to become a minus 1? It is most likely to become F minus. Right, so gain 1, and then its electron configuration would be that. This is that. All right, let's look at calcium. Let's do its electron configuration. That'll help us make a prediction. So if I have calcium, 2 ways you could write your electron configuration. You are more than welcome to do 1s2, 2s2, 2p6, 3s2, 3p6. Or what is a shortcut? I could skip to the end. Yep, let's bracket some argon. 4s2. All right, so how many valence electrons? 2. Is it likely to gain 16 to become minus 16? Or likely to lose 2 to become plus 2? They are lazy and they're envious, right? Everybody wants to be the noble gas. They're going to do their darndest to grab or throw away electrons to be like those cool noble gases over at the edge of the periodic table. See, the noble gases are so cool, they're hanging out the edge. It's like, outside school, too cool to like come in with everybody else. I have this whole play in my head about how the elements behave. I'm sure it's hilarious. Which 2 elements are getting together this week? Who's breaking up? Which elements are coming in to like ruin the covalent bond between other elements. It'd be good. It'd be like a soap opera of elements. Yes, that'd be amazing. Especially when you get to biochem, like there's all kinds of atoms that come in there to like mess up enzymes. They kick other people out, and then they make this new compound that's deadly. It's cool stuff. Yeah, like when you get heavy metal poisoning, it's because the heavy metal's coming in and kicking out the iron in your bloodstream and like just throwing it to the curb, but then when the heavy metal gets in there, it ruins the blood. It's fascinating. That's a whole other class though. Whole other class, we're off topic. Let's talk about sodium. All right, so sodium has how many valence electrons? 1. So is it likely to lose 1 or gain 7? 8, 7. 7, 6, 5, whatever I was counting. 1, 2, 6. 6-ish. All right, what about oxygen? How many electrons does it need to gain to become neon? 2. So is it going to be oxygen plus 2 or oxygen minus 2? Minus 2. Yay, go team. All right, what other kind of questions? Yes, ma'am, I'm ready.
Some examples of law of definite and multiple proportions.
Sure. Definite and multiple proportions. All right. So let's go over definite versus multiple proportions as a definition. No. Just a general question. General question from the audience. All right, let me make sure I have the exact same definitions I have in the notes. All right. All right, so for a given compound, or compounds in general, have a definite proportion of their constituent elements. That's always in the same ratio. I'll do the other definition, then I'll show you some examples between the two of them. If I have multiple proportions, means that when I have 2 elements, forming different compounds, the ratio of each compound is constant, but distinct from each other. All right, so for definite proportions, it means every time I make a given compound, the elements have to combine in the same ratio. So I'm going to make a sample of water. My water looks like this. You guys out there in the audience are going to make a sample of water. What's your water going to look like? Same. 3 years from now, we're going to make some water. What's it going to look like? Same. Every time I make this compound, so this is one specific compound, the ratio is always the same. So I've made one thing time and time and time and time again. It's always the same ratio. Law of multiple proportions says now I'm going to make two compounds using the same elements, but the ratios will be different. So I'm going to make some water. And then I'm going to make some hydrogen peroxide. All right, so I've made two compounds, both only H's and O's, but this is not the same compound as that. I could combine them in a crazier way where I could make I could do something like that. But they're really that's the same as that. But they're always different compounds, same combination of elements. I make 2 or 3 different things. So multiple proportions indicates that I have made 2 distinctly different things. Definite proportion means I've made one thing over and over and over again.
You wouldn't have to solve specific elements, which are like some things in the book where you're like specific grams of that ratio and you have to solve it out to find out what's specific.
Not for this test. I know there are some of those on the final. On this test, it's just going to be, does a sample of water and hydrogen peroxide obey the law of definite proportions, multiple proportion, conservation of mass, none of the above? It'll be something more like that.
Actual solve.
There will be no actual solving. I know for sure on the final there is actual solving, so we just need to work on that before the end of the semester. I'm going to do his question and your question.
You said the ratio of each compound is constant.
Mm-hmm.
So how could H2O2 be the same?
Oh, I'm saying it's constant to itself. So I make H2O2, you make H2O2. Those ratios are constant. Right, because these guys have to obey the law of definite proportions. These two are obeying the law of multiple proportions.
So hydrogen peroxide will always have 2 hydrogens, 2 oxygens.
Yes.
But hydrogen peroxide and water will not have the same
Ratio.
proportion.
Right, but they're still made with the same starter elements. So law of definite proportions is true for everybody. Multiple proportions is a relationship between 2 different groups of compounds. Similar question, different question? Okay.
Can we go over accuracy of the equation?
Sure. Just in general, like their definitions, how to calculate them, you will not need to calculate them. So save that for statistics class or analytical chemistry. But I'm not going to ask you to calculate accuracy or precision. Just if it's on the test, it's going to be real obvious. It's going to be something like, which I don't even know if I put it on there. So let's say you're out in the lab doing some measuring. We'll call them mass. I don't know what they could be. Let's say you're in there doing some mass measurements. Would you consider these 4 measurements precise? What is wrong with these 4 measurements? Which one would you throw out? The 8, right? Because something probably went wacky there. If you measured 4 4.5, 5, 8. You would probably hopefully think to yourself, wait a minute, did I zero this balance? Or am I putting two things on there? Because something has gone wrong, right? So precise. So if it's on the test, which I can't remember if it is or not, it's going to be that obvious. Like, for real, that is not precise. So. No, because that's a dumb skill. Temperature conversions. I'm assuming everybody can figure out temperature conversions. If not, we'll have lots more practice when we get to gas laws, going from Celsius to Kelvin, Kelvin to Celsius, back and forth. So, no, not in this test.
So if it were instead of 8.0, it was 4.0, would, so is there like a specific?
There certainly is. There's a whole class called statistics that can help us figure it out. We are not ready for that. So if it's on the test, it's going to be super obvious. Yeah, it'd be more like this probably. It's going to be something where you're like, whoa, wait a minute. I do not want that lab partner anymore. Because they are not using the scale correctly. So, yeah. Oh, yes, you.
Oh,
Sorry.
okay, wait a minute.
No, sorry.
Okay, this is probably a super simple question that you probably just went already so many times, and I don't get it. So if you have an element like calcium and
Yep.
it's in 4s,
Yes.
does that 4 mean in?
Yes.
So whatever s orbital it's in,
Whatever row it's in.
or row, okay?
Yep.
That's in.
Yes.
And then can you pick any number with L as long as it follows the rules?
Yep.
And so on and so forth. And then spin, does it have to be a specific one that we need to, like, do we have to figure out which way it's spinning?
You'll probably have to write an orbital diagram and do your Hund's rule and put all the ups first, then the downs. Right, so like what we have on the last quiz. Like, all right, so how would I go about figuring out what is the electron configuration of the very last electron I put in the sulfur?
If you remember.
It'd be 3p, and then what? So, right, S by itself is 1s2, 2s2, 2p, 6, 3s2, 3p, 4. I'm looking for that number 4 electron. So what would be... How do I tell you as the reader that I'm looking at the very 4th electron in the 3p level? What do you tell me? I can do it by arrows. I could draw a picture. But electron configuration says do it in letters and numbers. So that's going to be a hint. Electron configuration means letters and numbers. So I would tell you N equals what? 3. What does L equal if I'm in P? 1. And then... what's a good guess as to what M sub L could be? What are the rules? Right, so M sub L could be any of those. I'll accept any of those because you don't really know.
And you just picked L, right? You just.
I picked L because it was this. That tells me that.
Oh, okay, so if it was like D, would you put 2?
Yep.
Okay.
And then, because it's the 4th electron, in this case you may have wanted to draw yourself a picture just so you can picture it, or if that's 3p. Now I have 4 electrons. It would have to be negative 1/2.
Why wouldn't you combine them?
Why would I combine those? Combine what?
The last arrows, why wouldn't you combine them?
Oh.
Oh, yeah, you, no, that,
Oh, okay.
disregard that question.
Okay.
I'm so sorry.
No, that's fine. Disregard. So something like that where you're going back and forth between pictures, numbers, letters, things. Yeah.
On the periodic table, why does it start from like on the S, it starts like 1, 2, 3, 4, 5, and then like on the D, it starts from like 3 or something.
Okay. So why don't we see a d orbital until we hit scandium? So let's look at calcium versus scandium. All right, looking at those two options. If I look at calcium, what did I say? Oh, 21, sorry. 21. So if I look at calcium, what row is it in? 1, 2, 3, 4, 5? 4. So if it's in 4, what should the n value be? Okay. So it's looking at the 4 and what version of 4S, L, right? 4S comes first. And what does S tell me in terms of L value? 0, right? And so it happens to be 4S2. If I look at scandium, 3p ends at argon. Right now I'm at 4s2. But if I have an n equal to 3, 3, what are my values of L that are allowed?
2.
Yep. If I have a L of 0, that's S, right? That's P. That's D. So now when I get to scandium, my d orbitals are available where they weren't before because now I'm at an energy level big enough to handle them. So scandium is going to be N equals 3, L equals 2, which would be 3D1. Which would be the outer, well, it's the inner outer. It's a little tricky when we get to that part, right? Because 3, N equals 3 actually means less energy than N equals 4, but because it's D, it's slightly higher. This is why when you get to inorganic, you'll find out I've been lying to you about the transition metals. This doesn't work at all. Works great up to calcium. Then the rules get kind of wacky. But good for now.
It's in 4S, so why wouldn't N be 4?
Because scandium, like calcium's already filled up to 4s. Now I have 21 electrons, so the next electron has to go into 3D. Has to go into 3D. Yeah. Yeah, so scandium, right, it's actually argon.
For transition metals, can you assume that they're always one below the S orbital at their end?
It's like N minus 1.
Yes. Yeah. 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 Mackenzie.
For medium, does it have 3 valence or 1 valence?
3.
But the N value changes doesn't affect what we refer to as valence electron?
For mastering chemistry, that's what they say. That's not what I say, but they weren't asking me.
Alright.
So, yeah.